I'm picturing, something spinning, like a little tiny top.
Yeah, I guess it makes sense. The name kind of implies that.
Right.
But oh boy, are we in for a wild ride. Because the reality is, well, it's way more interesting
Hmm.
and definitely weirder than just a little thing spinning.
A lot weirder. Yeah, it's like, one of those fundamental concepts in physics that explains so much, but is so hard to wrap your head around.
Absolutely. And it really shows how our everyday experiences and our intuitions don't quite translate to the quantum world.
Yeah, totally. So for this deep dive, we're looking at this super cool article called The Enigma of Quantum Spin, Intrinsic Angular Momentum Beyond Classical Rotation.
Catchy title.
Right.
I like it.
So what we're going to try and do today is unpack this whole quantum spin thing. We'll explore, what makes it so strange, how it helps us categorize all these fundamental particles, and look at the evidence for it, because it's not just some, theoretical idea.
Yeah, we're going to break it down, make it as clear as we can.
Yeah.
But be warned, we're going to have to stretch our minds a little bit.
Yeah, a little bit. So to start off, where did this idea even come from? Like, was it just, some physicists sitting around, having too much coffee one day?
No, not quite. You see, the idea of quantum spin came about because, well, scientists were stumped. They had these observations they couldn't explain.
Oh.
Back in the early 1900s, they were looking at what's called the Zeeman effect.
Mm.
Basically, they were studying the light emitted by atoms when they were put in a magnetic field.
Okay.
And what they found was the patterns they saw in the light.
Yeah.
The specific wavelengths.
Right.
They didn't match up with their prediction.
Predictions based on what?
Well, they were thinking if electrons were just orbiting the nucleus, that's all there was to it.
Right.
But it seemed like there was something else going on, contributing to the atom's angular momentum and its magnetic behavior.
So, like, there was an extra ingredient in the recipe that they hadn't accounted for.
Exactly. Like they knew it had to be there, but they couldn't quite put their finger on it. So fast forward a bit to 1925, two physicists, Uhlenbeck and Goudsmit, come along and they propose this, well, radical idea.
Okay, here we go.
They said, what if electrons themselves have their own kind of intrinsic angular momentum, separate from their orbital motion?
Okay, so not just spinning around the nucleus, but also spinning on their own axis.
Yeah, and they called it spin. And this wasn't just some random angular momentum. They thought these electrons act like tiny, tiny bar magnets, each one with its own magnetic dipole moment.
A magnetic dipole moment. So that's kind of a measure of how strong a magnet is.
Exactly. So picture it like this. You have this tiny electron spinning on its axis like a tiny charged ball.
Yeah.
And because it's charged and spinning, it creates a magnetic field, just like a little bar magnet.
Okay, so far so good. So this picture of a spinning electron, it explained why those atomic spectra looked weird.
Right, it made the math work out. And it also helps explain why angular momentum was conserved inside atoms. It all seemed to fit.
But, and there's always a but with quantum mechanics, isn't there?
Yeah, there's always a but.
This neat little picture of a spinning electron starts to fall apart when you look a little closer.
Yes, it does. And one of the first big problems is the speed limit of the universe.
Ah, yes. The speed of light. The ultimate cosmic speed limit.
Precisely. Nothing can travel faster than the speed of light. It's roughly 299,792 kilometers per second. And here's the thing. If you take the electron's measured spin and its magnetic moment, and you consider just how incredibly small it is, like mind-bogglingly small,
Right.
then if it was actually spinning to produce those properties, its surface would have to be moving faster than the speed of light. Way faster.
Which, as we said, is a big no-no according to Einstein.
Exactly. And that right there tells us that quantum spin can't be about physical rotation in the way we imagine it.
Okay, so no tiny spinning ball then. But hold on, it gets even weirder. The article mentions that particles like electrons are treated as point particles.
Right, so in the standard model of particle physics, fundamental particles like electrons, quarks, photons, they're considered to have zero size. They're points.
So how can something with no size spin? Like, what's even spinning?
Yeah, that's the real head scratcher. It's like trying to spin a point on a piece of paper.
Yeah.
It just doesn't make sense in our usual way of thinking about things.
Okay, so it's not a tiny ball spinning. It's not even like a point spinning. And on top of that, the article says that quantum spin is quantized.
Yes, and that's another key difference from how we think about spin in the everyday world. Like imagine you have a top.
Okay.
You can spin it fast or slow. You can tilt it in any direction. But with quantum spin, it's not like that. It can only have certain specific values.
So it's like instead of a smooth dial, it's more like a light switch,
Oh.
either on or off.
Yeah, that's a good way to put it. It's discrete, it comes in set amounts, not a continuous spectrum. And this is where we get into the rules of the quantum game.
Quantum rules. All right, let's play. So the article talks about these quantum numbers, which sound kind of intimidating.
They do, but they're actually just a way to describe these allowed values of spin. The first one is called the spin quantum number. It's usually written as the letter S.
Yes, okay.
And this number tells us the inherent magnitude of spin, how much spin a particle has.
And this S can be any number.
Not just any number. It can be a whole number like 0, 1, 2, and so on, or it can be a half integer like 12, 32, 52. But it can't be just any random number. It has to be one of these specific values.
So it's quantized already at this level.
Exactly. And what's more, for a given type of particle, this S value never changes. Like every electron in the universe has a spin quantum number of 12.
Every single one.
Every single one. Every photon has a spin quantum number of 1. And the Higgs boson has a spin quantum number of 0.
So it's like a fundamental ID card for each particle.
Exactly. There's even a formula to calculate the actual magnitude of this spin angular momentum.
No, don't tell me there's math involved.
Well, just a little bit. But the main takeaway is that the amount of spin is not just any random value. It's fixed. And it's determined by this spin quantum number, S.
Okay, so we have this inherent amount of spin, but what about the direction? Like, is the spin pointing up, down, sideways?
That's where the second quantum number comes in, the spin projection quantum number, or MS.
Okay, another one.
Now, because of the Heisenberg uncertainty principle, we can't know both the magnitude and direction of the spin with perfect accuracy at the same time.
Of course, the uncertainty principle, always keeping things interesting.
Right, but we can measure the component of spin along a specific direction. Usually we pick what's called the z-axis, and the value we get for this component is determined by EMS.
Okay, so we pick a direction, and then we can figure out how much of the spin is pointing along that direction.
Exactly. And guess what? This value is also quantized.
No way.
Yes way. So for a particle with spin quantum number S, n's can only take on certain values. It can be s as s plus 1 and s plus 2, all the way up to plus s. So there are 2's plus 1 possible values.
Okay, that's a lot of numbers. Can we have an example, please?
Sure. Let's take our old friend, the electron. We know it has a spin quantum number S of 12.
Right, it's ID card.
Exactly. So if we plug that into our formula for M's, we get 2 possible values, plus 12 and Magesta 12.
So only 2 options, spin up or spin down.
Exactly. It's like a coin flip, but instead of heads or tails, it's up or down.
Quantum coin flip. I like it.
And here's another weird thing. Before we actually measure the spin, the electron is in a state called superposition.
Superposition. That sounds familiar.
It means it's in a combination of both spin up and spin down at the same time. Like the coin is spinning in the air before it lands. We don't know if it's heads or tails until we look.
So the electron is both up and down at the same time until we force it to pick a side.
Exactly. And then when we measure it, it collapses into one of those definite states, either up or down.
Mind-blowing. Okay, let's try another particle. What about a photon?
All right, so a photon has a spin quantum number S of 1. So if we use our formula, we get 3 possible values for M's, -1, 0, 0, and +1.
3 options this time.
Right. And these actually correspond to what's called the polarization of light. So +1 and -1 are circularly polarized light.
Circularly polarized, meaning...
It means the electric field of the light is rotating as it travels.
Okay.
And then 0, well, that's a bit more complicated for massless particles. It's related to the fact they can't have their spin aligned exactly along their direction of motion.
Right, right.
But the point is, even for photons, spin is quantized.
Okay, and one last one, just for fun. What about the Higgs boson? That mysterious particle that gives everything mass.
Well, the Higgs boson is a special case. It has a spin quantum number S of 0. So if we use our formula, we get only 1 possible value for M's, which is also 0.
So it doesn't spin at all.
Well, we say it has 0 intrinsic spin angular momentum. It's what we call a scalar particle.
All right, no spin for the Higgs. Now, this whole thing about integer versus half-integer spin, the article makes a big deal about it.
And for good reason. It turns out this seemingly small difference has huge implications. It's how we classify all fundamental particles into 2 main groups, fermions and bosons.
Okay, fermions and bosons, those names ring a bell.
So particles with half-integer spin like 12, 32, 52, and so on, they're called fermions, named after Enrico Fermi.
Okay.
And particles with integer spin, like 0, 1, 2, and so on, they're called bosons, named after Satyendra Nath Bose.
Okay, so two teams, half-integer spin, fermions, integer spin, bosons. What's so important about that?
Well, it turns out these two groups, they play very different roles in the universe, and they behave very differently. Like fermions, they're the building blocks of matter. All the stuff we see and interact with, it's made up of fermions.
So me, you, this table, all fermions.
All fermions.
Yeah.
At the most fundamental level. Yeah, so we have quarks, which make up protons and neutrons. And then we have leptons, like electrons, muons, tachyssus, and neutrinos. And anything made up of an odd number of these, like protons and neutrons themselves, they're also fermions.
Okay, so lots of different types of fermions, but they all have this half-integer spin. And what about their behavior? What makes them different?
Well, the big thing about fermions is they follow this rule called the Pauli exclusion principle.
The Pauli exclusion principle. Sounds serious.
It is. It's basically like fermions have a personal space bubble. It says no two identical fermions can occupy the same quantum state at the same time.
Okay, so like they can't all be in the same place doing the same thing?
Exactly. Like imagine electrons in an atom. They can't all just crowd into the lowest energy level. Because they have different spins, they have to occupy different energy levels in orbitals.
Ah, so that's why atoms have that specific structure, with electrons arranged in shells and stuff.
Exactly.
Hmm.
The Pauli exclusion principle, it's the reason why matter has volume, why things don't just collapse in on themselves, why we can have chemistry, the periodic table, all of that, it comes down to this principle.
Wow. So this quantum spin thing, it's responsible for like the structure of the entire universe.
Yeah, pretty much. And it gets even crazier. The article mentions that in extreme environments, like in white dwarf stars and neutron stars, the Pauli exclusion principle is what's holding them up against gravity.
So it's preventing them from collapsing into black holes.
Exactly. It's like the quantum scaffolding that's keeping these incredibly dense objects from imploding. Pretty cool, right?
Crazy cool. So fermions, they're all about personal space. They make up matter. What about bosons? What do they do?
Bosons, they're the social butterflies of the particle world.
Meaning?
They don't follow the Pauli exclusion principle. They can all pile into the same quantum state, no problem. And this leads to some really interesting phenomena.
Oh, like what?
Well, think about lasers. A laser is basically a bunch of photons, all in the same quantum state, all with the same energy, same direction, same everything.
That's possible because they're bosons.
Exactly. They can all hang out together, no problem. And that gives us this incredibly focused, powerful beam of light.
Wow. Okay, what else?
Then there's superfluidity.
Superfluidity, like superfluids.
Yeah. So certain fluids, like helium-4, when you cool them down to super low temperatures, they become superfluids.
Meaning?
They can flow without any resistance, no friction at all. And this happens because the helium-4 atoms, they're bosons. So they can all condense into the same quantum state and just glide along.
Like a quantum slip and slide.
Exactly. And then there's superconductivity, which is kind of similar. Some materials, at low temperatures, electrons can pair up, and these pairs act like bosons.
So they can all be in the same state?
Yep. And this allows electricity to flow through with zero resistance.
So no energy loss. Super efficient.
Exactly. And then we have Bose-Einstein condensates, which are even weirder.
Okay, I'm listening.
So if you cool a gas of bosons down to near absolute zero, they could all collapse into the lowest possible energy state. Like, they all become one big quantum blob.
The quantum bow.
It's like they lose their individual identities and act as one giant quantum wave. It's a macroscopic manifestation of quantum mechanics.
So all this from whether a particle has integer or half-integer spin.
Mind-blowing, right?
Totally. But how do we know any of this is true? Like, how do we actually measure spin?
That's a great question. And it brings us to one of the most famous experiments in physics, the Stern-Gerlach experiment.
Okay, I've heard of that.
It was done back in 1922, and it provided the first direct evidence for the quantization of spin.
So what did they do in this experiment?
So they took a beam of neutral silver atoms, and they fired it through a specially shaped magnetic field.
Okay, why silver?
Well, silver atoms have this one unpaired electron in their outer shell, and that electron gives the whole atom a magnetic dipole moment. Basically, it makes the atom act like a tiny magnet. And they used neutral atoms, so the magnetic field wouldn't just deflect them because of their charge. They wanted to isolate the effect of this intrinsic magnetic moment.
Okay, smart. So they fire these silver atoms through a magnetic field. What kind of magnetic field?
Not just any magnetic field. They use what's called an inhomogeneous magnetic field. It means the strength of the field is different at different points in space.
Okay, so it's not uniform.
Exactly.
Yeah.
And they did this by shaping the poles of the magnets in a special way.
Okay, I'm picturing it. So they send these silver atoms, which are like tiny magnets, through this weird magnetic field. What happens?
Well, here's the thing. If the spins of these atoms were just randomly oriented, like pointing in any direction,
Yeah.
then classically you would expect the beam to spread out smoothly. Like you get a continuous smear of atoms hitting the detector.
Okay, so kind of a blurry line.
Right. But that's not what they saw.
Oh.
Instead, they saw the beam split into two distinct spots.
Two. Just two.
Just two. And that was huge, because it meant the magnetic moment of the atoms, and therefore their spin, could only be in one of two orientations.
Up or down.
Exactly.
Oh.
This is the first direct evidence that spin is quantized. It could only take on these specific discrete values.
Wow. So this seemingly simple experiment, it revolutionized our understanding of the nature of angular momentum.
Totally. And it showed that the quantum world plays by very different rules than the classical world.
Yeah, no kidding.
Yeah.
The article goes on to talk about how this whole spin thing is connected to other big theories in physics.
It is. It's not just some isolated idea. Like, there's the Dirac equation.
Okay, remind me, what's that again?
Well, it's a really important equation in physics that combines quantum mechanics with special relativity. And the amazing thing is the idea of electron spin with its specific value of 12, it just pops right out of the equation.
So it's not something they had to add in, it was already there.
Exactly. It's a natural consequence of combining those two fundamental theories. And that suggests a deep connection between spin and the structure of space-time itself.
Okay, that's pretty deep.
And then there's the spin statistics theorem. It's a theorem from quantum field theory. And it says that all particles with half-integer spin are fermions, and they obey the Pauli exclusion principle. And all particles with integer spin are bosons, and they can occupy the same quantum state.
So this theorem connects how much spin a particle has to how it behaves in a group.
Exactly. And it's one of the fundamental principles of modern physics.
Wow. Okay, so just to summarize for our listeners, what are the key takeaways about this whole quantum spin thing?
So first of all, it's not about physical spinning, even though the name suggests that. It's an intrinsic property of particles.
Right, no tiny ball spinning around.
Right. It's more like an inherent amount of angular momentum that each particle has.
And this angular momentum, it's quantized, meaning it can only take on certain specific values.
Exactly. And those values determine whether a particle is a fermion or a boson.
And those two types of particles, they behave very differently. Fermions make up matter, they have their personal space, and bosons, they can all be in the same state, leading to all sorts of weird and wonderful phenomena.
Exactly. And all this comes down to this seemingly simple property of quantum spin.
So even though it's a bit mind-boggling, quantum spin is a fundamental part of how the universe works.
It is. And it shows us that the world at the smallest scales is far stranger and more fascinating than we could ever have imagined.
Absolutely. Now, for our listeners, here's something to ponder. Think about all the incredible things that spin makes possible, from the stability of atoms to the existence of lasers and superconductors. What other mysteries of the quantum world might be shaping our everyday experience in ways we don't even realize? It's a question worth exploring.